afternoon, everyone. My name is Julia Holgado. I'm a senior software engineer at New Relic, and today I'm going to talk to you about how we approach Kafka replication at scale. So one of the easiest ways I find to present ideas is to go through a narrative. That narrative today is New Relic's cloud migration with a focus on how we decided to replicate data in between different Kafka clusters. There's a couple stages of that, such as the different types of routing we discovered, starting with one-to-many, and then how we adapted our solution for that to go to different types of routing as we introduced more clusters to route data in between. And I'm going to wrap up with the ongoing improvements we are making to that system. So if you haven't heard of New Relic, we are a monitoring and observability company. We're taking in data from engineers all over the world. And just to give you a sense of the scale that we're operating at, that 150 plus petabytes per month, that is all going through Kafka. But we didn't always operate at that scale. Part of why we're able to do that is because of our migration to the cloud and utilizing many different Kafka clusters. At the very start of our cloud migration, or before even introducing anything to the cloud at all, this is a really simple view of what our architecture looked like. We have data coming in through HTTP endpoints. They go into our ingest tier, where they're eventually put into Kafka, and they're transformed, aggregated by our pipeline services, and then they find their way onto the insert workers, where they're then placed into the New Relic database and then presented to our customers via our APIs and UIs. Now, something to note, I didn't do a very good job of portraying this right here, but at its largest, our on-premise Kafka cluster was over 200 brokers, somewhere around maybe 240. Very unwieldy to maintain. So when we were moving to the cloud, what we wanted to do was break up that cluster. And the objective of moving to the cloud as well was to implement a cellular architecture. Now, starting out, our definition of cells was a smaller version of New Relic. So we still had our data center, we still had data going into the data center, and then we started to send data into our cells based on particular data types or the account ID. Now, how do we do that? Around this time, we also introduced a service called Wayfinder, and that is a service when, as data comes into our HTTP endpoints, we give it the account and the data type, and Wayfinder is going to tell you whether that data is going to go to the data center or to a particular cell. Something else we get from Wayfinder is that we can tell it, stop sending to a particular cell. This is good because these cells come and go, and sometimes they have problems. We want to be able to route data away from a cell, send it to a different one. So at this point, we could have the situation where a customer's data is going into the data center, and maybe they have a different data type going into cells. So maybe, let's say their custom events are going into the data center, and maybe their metrics are going into this bottom cell. We have a lot of pipeline services that make the assumption that all of a customer's data is going to be in the same Kafka cluster. Of course, that's not the case right now. So we need to get that data that's going into the data center and make it available to the pipeline services in the cloud as a way of starting to drain that data center. So one way we might do this is mirror that data. But we might also have another customer for which that has that exact same situation. So, okay, well, we could mirror that data. And then, well, at that point, we just end up mirroring all customer data from the data center into these cells. The problem with that is, again, these cells are supposed to contain smaller Kafka clusters. They are smaller versions of New Relic, and so if we just mirror everyone's data into the cells, they're not going to be able to take it. They're just going to fall over. The other problem with this has to do with that ability to route data away from a particular cell if it's having a problem. So, if we want to alter that routing for the customer represented by the orange arrow, well, we could probably take down that mirror, and then we'd probably have to make some changes about where that mirror for that customer is going. But then we'd have to do that every time a cell is having a problem, every time we want to tear down a cell, or maybe when we bring up a new cell, we want to have that customer sent somewhere else. And that's a lot of toil. So gathering some of the requirements that we found for getting data out of the data center and into the cells, one-to-many routing, we want that failure isolation. And then we want to react to any changes without having to mess with any deploys. These two on the bottom I haven't quite discussed yet. The first has to do with routing based on the account ID and the data type in a Kafka message. And one thing about how we represent data at New Relic is that we'll put certain metadata in the Kafka header. So then potentially a service could look at the Kafka header, see what type of data and whose data it is, and then make a decision on where that data is supposed to be sent based on that information. And then this final one, being able to support multiple routing strategies. We have a lot of different topics at New Relic, a lot of different services. They need to be sending that data in, of course, different ways. So should be able to support a particular routing strategy for one topic and a different one for another topic. So what we decided to do was create some sort of smart mirror, something that would consume a particular Kafka topic in the data center, make a decision on each message, and then produce that message to a particular Kafka cluster associated with one of our cells. And this is the system we came up with. We called it Synapses. It's a combination of Kafka and synapses, excuse me. And the main parts of it are the router on the left and the mirror on the right. They're both Java services, and they just create Kafka clients, consumers and producers. And they're connected by Kafka topics. We call these routed topics. I'll get into a little bit more in just a moment. And at the bottom, we've got some dependencies. The router is mainly responsible for consuming from source clusters, and the mirror is responsible mostly for producing to the destination clusters. So I'll start by getting into the router first. On startup, the router is going to connect to S3. S3 is where we store all of our configuration information. So which topics, how those topics are going to be routed, which Kafka clusters those topics are going to be found in. Once it does that, once it discovers those topics, it's going to create a routed topic in an intermediary Kafka cluster, and they're named a specific way. They're going to be named the destination dot the source topic name. And those represent each destination that source topic can go to. After creates, and each of those is pretty much a copy of the source topic. Once it creates those routed topics, it's going to create a number of consumers based on the number of source topics. So in this example, there's only one, so it would only create one consumer for topic A, but say if topic A had another source cluster, it would create another consumer for that. It also interacts with our cluster inventory just as a sort of sanity check, to double check that the source clusters are actually available to be consumed from. And then it's also going to communicate with Wayfinder. Because there are certain topics that require routing based on the account and the data type. So for topics that require that kind of routing, it's going to make requests of Wayfinder to ask, hey, which cell do I send this piece of data to? So to go through a quick example for the router, it starts up, discovers it needs to connect to topic A in cluster A. It's going to create a consumer for topic A in cluster A, and then, but it's also going to create those routed topics. Once it starts consuming, it's going to take a message, decide where that message from topic A in cluster A is going to be routed based on the routing strategy configured for topic A, and then it's going to produce that message onto the routed topic. So for example, if the message we're talking about is destined for topic A in cluster B, it's going to produce that message to the cluster B dot topic A routed topic. After that, it's going to be consumed by the mirror. The mirror is similar to the router because on startup, it's going to check for the set of topics that it needs to handle in S3. It's also going to connect to our cluster inventory as, again, another sanity check to make sure that the destination clusters are actually available to be produced to. It doesn't make any decisions on the routing save for when it consumes a message off of a routed topic, it's going to produce that message to a destination cluster based on the name of that routed topic. So building on the example from the last slide, if it consumes a message from the cluster B.topic A routed topic, that message is going to get produced to topic A in cluster B. So how does that information get into S3? So we just maintain a GitHub repository, and that's just a collection of YAML files. And each topic is going to have a file for the router and a file for the mirror. And that is going to contain information like the topic name, the source clusters that topic is going to be found in, and the routing strategy, the logic the router is going to use to determine which destination to send that topic's data. And we rely mostly on our client teams to decide whether or not they want a topic routed by Canapses. So when they do decide that, they open a PR into this repository. And once it's merged, we have automation that saves all of that information into S3. And as the routers and mirrors are running, they're eventually going to pick that up. Something else that we get from this configuration is that we also allow configuring clients. So you can set particular consumer and producer configurations for the router for a particular topic. You can do the same for the mirror. In terms of knowing where to route it, so how does it get in, or how does it have the information to connect to a particular cluster? As part of our automation for standing up Kafka clusters in particular cells, we're going to just write that information to S3 as well. So the name of the cluster, the security protocol, the connection string, anything Canapses will need to consume from or produce to that cluster. So this is a diagram of what our architecture sort of looks like when we first introduced Canapses. It's a little bit misleading in that I have the routed topics separate from the data center's Kafka cluster, but that is where they are created. And at this point, we had not too many destination clusters, not that many topics. So now I'm going to get into the problems we encountered when we introduced Canapses here. And the first is the partition explosion. I mentioned that the router creates a copy of the source topic for every destination. So it might not be a problem if a topic does not have a lot of destinations. Maybe it has a pretty low partition account, like 5. But again, at New Relic, we have topics used for all sorts of purposes, and they have all sorts of sizes in our data center. I think our largest topics got up to 400, maybe a little bit more than that partitions. So we could not just keep creating copies of very large topics. So that's going to create a lot of load on the brokers. But moreover, something to keep in mind is that Canapses does not make any decisions about how to distribute itself between the topics it handles. Meaning that in the mirror specifically, where this problem becomes a little more apparent, the mirror is just going to discover all of the routed topics, and it's going to try to consume from all of them. So when a mirror restarts, it's going to cause a huge rebalance storm across all of those routed topics. And at New Relic, our customers need to be seeing their data in real time. And these rebalance storms often could take anywhere on the order of minutes. And that's way too slow for what we need to be providing for our customers. We did limit this a little bit by putting a cap on some topics, some pretty large topics. So say, in that 400 partition example, don't create any more than 100 partitions for that particular topic. And then another problem that we dealt with was that there are topics of varying size and traffic that Canapses is handling. Again, it's not going to make any decisions about how many instances to start to consume that will be used to consume from a particular topic. So, it might be the case that we have a topic that's really large, has a lot of traffic, and probably could use more instances of the service consuming from it, but it just doesn't have that logic. Every router is going to try to consume from every source topic. Every mirror is going to try to consume from every routed topic. So this is just a recap of the problems I've gone through so far. There's that partition explosion, that more bloat on the Kafka brokers, and then causing those rebalance storms when we have to roll a mirror or when a mirror restarts. And then this problem of being unable to steer more resources towards more heavy topics. And what we did to kind of lessen the impact of that was introduce sharding. And that's just separate deployments of Canapses that handle a particular set of topics. So we might assign maybe some very low throughput topics to one shard, and then maybe even a high traffic topic gets its own shard. And this way, we can size those shards for the topics that they are handling. And then if a mirror restarts on one of those shards, it's only the routed topics that that shard for that mirror was handling that undergoes a rebalance. The downside of this is that while the number of topics that Canapses is currently handling is small enough that an engineer can manually assign it to a shard, we are still at that stage where we are manually assigning topics to a shard, and of course that's a lot of toil to keep working on. So now we're starting to drain more data out of the data center. We're starting to get more pipeline services out of our data center and into cells. And it's at this point that our definition of cells changes. Rather than each cell being a smaller version of New Relic, a cell ends up being thought of more as a Kafka cluster and a collection of client services that interact with it. What this meant is that we started segmenting our pipeline sort of based on where the service was in processing data, or maybe what type of data the services were processing. So in one example, we could have an ingest cell type, and that's a bunch of services that are interacting with the data right after they come off the ingest tier. And then we could have an aggregation cell type. So those services could be a bunch of stateful services that are calculating aggregations to be evaluated for alerts. And when we started segmenting our pipeline services like this, that's when we started discovering the need for more types of routing beyond the one-to-many that I've just gone over. So as an example of many-to-many routing, building on that ingest cells into aggregation cells example, we could have a customer's data being spread across 3 different cells. In order for aggregations, say for alerts, for that customer to be correct, all of that data needs to be sent to the same aggregation cell so that it's processed by the same service. So we could have all of these ingest cells needing their data to be sent to a particular aggregation cell. But if that one aggregation cell goes down, we don't want it to be the only one that was processing the aggregation for that say a particular alert. We don't just want to lose any aggregations that we had. So we are also going to send it to a second cell. And then say if there's another customer, we might have more connections that look like this. As a one-to-many example, we have services that will collect data from sub-accounts, generate data based on that, and then publish it to the root account. So these services, again, because they started out in the data center, they had that assumption that all of the accounts are in the same Kafka cluster. With that not being the case, so for example, we could have the sub-accounts coming into these top 3 cells, they need to go into the ingest cell that the root account is arriving in. So then we need to have data flow like this, the top 3 cells going into that bottom one. So when thinking about the connections between the different cells, so just going very generic here, we could have cell A connecting to cells of type A connecting to all the cells of type B. So maybe we could have maybe a pull mechanism where, say, the router sits in source cells and the mirror sits in destination cells, and the mirror is going to pull data off routed topics. Or maybe we have a push model where Canapses sits in all of the source cells and then pushes data to the destination cells. If we try that, we'd have to keep all of these connections up. And depending on how you've set up networking between your Kafka clusters, this might not even be possible. What we went with instead was to introduce a routing cell. And that's just going to be a cell whose contents are a Kafka cluster and Canapses. And it's going to connect to, again, all the source cells and then produce to the destination cells as shown. So this is very roughly what our architecture looks like with a routing cell in the middle. It's maintaining multiple connections to cells of all different types. And it's at this point that we've more than doubled the throughput that Canapses is using ever since its inception. So now let's go into some of the problems that we encountered when using Canapses in this context. And the first is loops. This is a tough one. We don't really have a good way of solving it just yet. Canapses has a way of detecting, that first hop, if it consumes a message, and then through whatever routing strategy it was using, it determines that that message has to go back to the same topic in the same source cell. It's just going to drop it. It's not going to produce that message. But, we could have a situation where Canapses consumes a message, produces it to a destination cell, and that in that destination cell, that message maybe finds its way to another topic that Canapses handles, and then maybe that gets produced back to the original source cell. Something else to keep in mind is that some teams don't use Canapses to replicate data in between cells. They operate their own mirrors. So this, with Canapses being unaware of the many different pathways, in addition to pathways that are completely separate, it makes it hard to detect loops here. The other problem is the cost of that intermediary Kafka cluster we started introducing with the routing cells. This didn't really manifest itself in the data center because we were already paying for those machines. It was really more of a case of, are we using all of their storage or not? But as we are moving more of our pipeline services into the cloud, as more teams discover that they need to replicate data in between different cells, we're going to add more topics that Canapses handles, more traffic, more partitions, and that intermediary Kafka cluster just keeps getting larger and larger, and so costs more. And then there's this other problem of this central point, and it comes from basically the idea that we have to send data in between Kafka clusters. So Canapses is set up such that if a source cell has a problem, it can consume from the other source cells just fine. Similarly, if a particular destination cell has a problem, it can produce to the other destination cells just fine. But if there is a problem in the intermediary Kafka cluster, in that Kafka cluster in the routing cell, all of the pipelines are going to be impacted. We've sort of lessened this impact by introducing multiple routing cells. So, if a routing cell has a problem, we can just tear down all of the Canapses routers in the routing cell that's having a problem, and then because Canapses instances across shards will use the same consumer groups, the Canapses routers in the other routing cell, the functional one, will be able to just pick up the traffic that the other one was handling. So I've talked a little bit about how we've routed data in between different Kafka clusters, and the problems that we've been encountering. So I'm going to talk now a little bit about how we're trying to make it better. So I mentioned that the cost of the intermediary Kafka cluster is getting pretty high, and it's also kind of that central point of our architecture. So we're kind of reevaluating our use of it. We're wondering, is there something else we can do that still lets us back pressure, that still lets us store data if we encounter problems with producing or consuming data? So, maybe we don't use something that's provisioned and sits there the entire time. Maybe we just create storage as needed. Or maybe we don't need to split the router and the mirror anymore. Maybe they should just be the same service and then rely on back pressuring into the source topics. This next one is one I can talk a little bit more about because this is something that's actively being worked on right now, and this has to do with the problem that Synapses doesn't have any logic to distribute itself across the different topics. Again, each router is going to discover the set of topics that it needs to handle, and then it's going to just connect to all of them. But sometimes maybe a topic doesn't need every single router to be trying to consume from it, and maybe some topics need more than one. So we want to see if we can get Synapses instances to assign themselves to a particular topic. And that way we can size the instances better, so maybe they have better CPU, they have more efficient CPU usage, and then the end goal is to remove the operational toil of shards. So in considering ways Synapses might be able to assign themselves to a particular topic, we started looking at hash-based algorithms. The first of these is simple modulus, and each router is just going to take the hash of its instance name and then mod it by the hash of the task name. For the routers, this task name is going to be just a concatenation of the source cluster and the source topic. And it's going to run that calculation for all of the tasks, all of the topics, and then it's going to claim the one for which that calculation is the highest, and then every router performs that calculation. Another one that we looked at was consistent hash, and we just take the hash of the task name and then assign it to a bucket, and the buckets in this case are just the router instances. And again, every router performs this calculation. It's going to just take all those task names and see, hey, which ones belong to me. This last one, weighted rendezvous, it's something that's more commonly used in load balancing where you assign particular tasks to a node, and each of those nodes have a weight. We've sort of reversed it we've reversed it by making the tasks weighted in an effort to make it more likely that a router is going to be assigned to a particular topic. So say we've got 2 topics with a weight of 3, 2 topics with a weight of 1. So those topics with a weight of 3 should be assigned 3 times the instances that the weight of 1 gets. So the hope is that the assignment would look something like this. And then the last method that we looked at, it's not hash-based, but it's another way to get Synapses instances to assign themselves to a topic, was random latch. And we used Zookeeper for this. We represented each topic as a node in Zookeeper, each task as a node in Zookeeper. And then each Synapses instance attempts to just randomly picks one and attempts to claim leadership of that. And eventually, one instance does claim leadership of a particular node. But you can see here we've got 4 idle instances. So this doesn't really make efficient use of the resources Synapses has. And something that we found out when testing out the hash-based algorithms is that those also ended up having a poor distribution of tasks. We could have idle routers. We could have instances that only had 1 task. Meanwhile, there are instances with 6 tasks, maybe more. So it was at this point we needed to find a way to get a more even distribution. And then what we settled on was trying a coordinator-based approach. And that means When a change happens that requires a recalculation of the work assignment or the task assignments, such as change in the worker set, maybe an instance goes away, maybe we added more instances, maybe more tasks were added, tasks were changed. The set of instances elects a coordinator, and that coordinator is in charge of calculating that task assignment. Once that task assignment is calculated, it's going to place those assignments in some spot where all the other routers can see them. So maybe that's Zookeeper, maybe that's some other data store. And the exact algorithm for that is something we're still working out. So we've reached the end of the talk now. I've taken you through how New Relic has approached replicating data between different Kafka clusters, some of the difficulties we've encountered partially due to how we've implemented cellular architecture, partially due to how we've accomplished routing between different Kafka clusters, and how we're trying to make that better. And hopefully I've given you an interesting take on this problem and maybe given you an idea for your own architecture. Thank you so much.